Good afternoon and welcome to today's webinar titled Understanding Particle Counts and Setting Target ISO Codes. My name is Taylor Colon. I am a Customer Engagement Specialist here at TestOil. I'll be your host today. Before we get started, there are a few things I wanted to go over. First, everyone is muted. We are recording today's presentation, and by being on mute, this will ensure high quality recording. Second, please feel free to use the questions box in the GoToWebinar application. We would be happy to answer any questions that you may have. Finally, the webinar recording will be distributed later today along with a survey. Look for that in the email that you registered with. Let's get started. Today's webinar is presented by Evan Zabowski. Evan is a certified lubrication specialist and a senior technical advisor here at TestOil. All right, Evan, are you ready to go?
I am. Thank you, Taylor.
You're very welcome.
So as he said, today's presentation is about understanding particle counts, which will be about half the presentation, and then we'll finish up with a little bit on setting target ISO codes. But before I get into any of that, I thought it would be best if we actually begin with a discussion about why we're so concerned about particulate. Like, why are we doing a particle count in the first place? And that helps us understand to a point what we're trying to achieve here. So I've got three different studies I'd like to show you. They're all widely cited. Lots of people have used them, so you might have seen some of these before. The first one's kind of one of my favorites. This one's by Dr. Rabinowitz, and he was working at MIT, and he did quite a few good studies. This one, he was looking into the causes of premature, and he used the word failures initially, but most correctly, he termed it as a loss of usefulness. This came out of the Nolan and Heap report when they were suggesting that the word failure needed a better definition, because most people attribute the word failure to a component basically blowing up or ceasing all operation. They suggested that really a failure was defined as when something doesn't operate the way it should. And that was a definition that was further expanded by John Mowbray when he wrote the Reliability-Centered Maintenance, basically the Bible that we all use. So Dr. Rabinowitz was using that same terminology, a loss of usefulness. And he said, what's the greatest cause for loss of usefulness? And as you follow this to the right, you can see that surface deterioration is the #1 out of the three choices. And he chose the word surface deterioration because that's not just a fancy way of saying wear, but it's because he wanted to differentiate the type of wear. So again, if you move to the right, we see that wear, meaning like physical wear, is the biggest cause of surface deterioration, more so than, say, corrosion. Now, of wear, one of the largest slices of that comes in the form of adhesive wear, as you can see, but also abrasive wear. And of abrasive wear, the largest slice of that seems to come from what we call three-body abrasive wear. Now, the difference between three-body and two-body is with two bodies, you have two metal surfaces coming into close contact with each other. One surface rubs the other one, and one of the two surfaces will lose. Basically, it's your sandpaper and wood kind of comparison. But three-body abrasion is when you have those two surfaces coming into close contact, and they may or may not contact each other, but they will have some form of particulate in between them, and that will be rubbed against both surfaces. And again, at least one of those two surfaces will lose, and that's where we start to see the wear. So the point of this study is that the largest slice of the largest slice of the largest slice is particulate related. And that's why we get so concerned about particulate contamination, is because it can be attributed to a significant amount of the wear or loss of usefulness that we experience, but it's also one of the most easy to control. Now, one of the other studies that exists out there, this one's from the National Research Council, and it was trying to define how, I guess, the economic impact of various types of wear mechanisms. And as you can see, the largest slice of this is abrasion, which is your two and three body abrasive wear. Then there's adhesion, which is no surprise based on the previous study, but also let's include erosion. Now, erosion is the same as sandblasting, so this is when particulate is flowing in the oil, and it either encounters an orifice or a rapid change in direction, like an elbow, and the particles will impinge on the surface and create wear. Now, of those three slices of this particular pie, they total 82% of the economic impact due to wear. So that's where we're getting the title that 82% of wear is particle induced, because these are all going to be accelerated or only capable because of particulate. The one last study, this one's from a bearing supplier, and it identifies the most common causes, and the key word here is premature bearing failure, because all bearings eventually by design should fail. But if they don't reach their L10 life and they fail early on, the largest causes for that are, again, you guessed it, contamination. So this is why we're so concerned about particulate contamination, is that we know no matter what studies you look at, no matter what the percentages work out to be, it's always the largest slice of the pie. And like I said, it's one of the most, one of the easiest to control, one of the easiest to justify, and one of the fastest reacting changes we can make to a system is to improve its cleanliness and see that we're reducing wear and increasing uptime and all the good things that we're looking for. So the next question basically comes down to, well, how big is this particulate? I mean, we know particulate's the problem, but how big is it? Because we need to know how big it is if we're going to try and find a way to mitigate it or remove it in any way. So just to begin with a quick definition, so nobody's in the dark here, I'll be using the term micron. For those that aren't familiar with what a micron truly works out to be, it is 1/1,000,000th of a meter. And whether you say micron or micrometer or millionth of a meter, they're all the same thing. There's no difference. For those of you who work in the imperial system, it's about 0.04 of an inch. So we're talking about a pretty small particle here. Just to give you the visual comparison, human hair is often used as a good example. It's about 80 microns as a cross section. When we start thinking about dust, it's about half as big. Now, when we talk about dust and we mention this 40 micron value, often this is cited as the lower detection limit for the human vision. 40 is the approximate limit of somebody who's perhaps over the age of 40. But if you're a little bit younger, or if you do have decent eyesight and don't use corrective lenses, you can truthfully see down to about 25 microns. But whether or not you stick with 25 or 40, it doesn't really matter. The point is you start getting smaller and smaller, we start getting into the range of powders and airborne contaminants. And this is where we will concentrate. So just to show you what size we're going to be dealing with, here's one study. This is done now by a bearing supplier, and it's showing the effects of filtration on bearing life. So we can take this kind of at face value, because this isn't data from a filter supplier trying to sell us filters. It's from a bearing supplier trying to encourage you to filter your oil so that you'll get the proper life out of your bearings. So if you start reading this chart at the far right-hand side and work your way left along this line, what you can glean is that with approximately 40 micron filtration, we're going to expect 3 million cycles out of the bearing as a life. If we can go all the way down to 10 micron filtration, we might improve that to 5 million cycles. If we can get down to 5 micron filtration, we're going to bump that up to 8 million cycles. And if we can get all the way down to 1 micron filtration, we could achieve 13 million cycles. So one way of interpreting this chart is that switching from 40 micron filtration all the way down to 1 micron filtration would give us a 4 times life extension. The other way to interpret it is that that might be a bit extreme, might not be feasible or practical or economical to try and achieve that. But basically, if you look where the major inflection begins on this curve, if you're not filtering at least greater or smaller than 10 microns, you're really not improving much of the bearing's life. So we are talking about some pretty fine filtration yielding some positive results. So then the question is, well, what's the most damaging size of particle? Well, there's a couple different answers that have been published to this question, and here's 2 of them. The top one says 2 to 22 microns, and the bottom one says 1 to 5 microns. Now, at first glance, you look at these answers and you say, that's not the same answer. But if you think about it a little bit, it is the same answer. They're actually in agreement, these 2 numerical values. You're just not interpreting them as what they're meant to represent. You're looking at them as absolute values and thinking that they're off by a factor of 4. But really, what we're seeing here is that we're talking about very, very small particulate. These are the types of particles that actually cause the damage. The larger ones really are of little concern to us because they typically don't cause that much damage. Because the best answer to the question of what is the most damaging size particle is clearance size particles. And why are we so concerned about clearance size particles? Because they are the ones that cause that 3-body wear. If a particle is larger than clearance, it can't get in between 2 metal surfaces. If it's smaller than clearance, it'll go through without contacting either surface. But if it's at or near the clearance size of the 2 parts in motion, well then, we've got a particle that can impinge upon one or both surfaces, causing some damage. And that, of course, is everything we're trying to avoid. So to show you why those 2 answers on the previous slide are kind of the same answer, just take a look at the typical clearances that can be found in many types of components. They do bracket within that 1 to 5 micron statement. And to be fair, they also fall heavily within that 2 to 22 micron statement. So the point is, we're dealing with clearance-sized particles. Those are the ones that are damaging. Those are the ones we need to be concerned about. Now, the next question typically we have is, even though we know that we need clean oil, we know we want to deal with small particles, we now have this question: where is it all coming from? Because if we know where it's coming from, then maybe we know how we can deal with it. Because some of it we might be able to stop from ever happening, and some of it we have to take different measures because of where it's being created. So basically, there's going to be about 3 sources. It's either coming from the outside, it's being generated on the inside, or it was there long before we even got there. So just to walk you through a few of these, I'll spend most of my time on the internally generated because that is of the greatest concern. But I'll walk you through some examples of where they come from in all 3 cases. From external sources, we have everything that could be airborne. So there's a lot of process-related debris that occurs depending on what you have the machine doing. So if we have the machine operating in an outside environment, well, certainly there's the ability that there's airborne dust. But what if the machine's actually creating this dust? It's not just from the atmosphere. So I've listed a few things in the process-related column. And the things I've listed over in the environment are what do we have as mitigation strategies. Right? We know this is in the environment. Even if it's not process-related, there's still going to be airborne contamination. Well, we have all these strategies to hopefully deal with them. Right? We put breathers on them to try and allow the machine to breathe, but not breathe in a lot of this dust and dirt and whatnot. We might have seals around certain openings or shafts or things like that. We have, of course, a way of getting oil in, and we might even have inspection covers. But basically, any dipstick, oil plug, fill cap, cover hatch, you name it, is a potential path for the particulate to get in, and anything that may be in the atmosphere is, of course, deemed a contaminant and we're trying to avoid. But the internal ones, these are the ones that are of greater concern to us because these ones are harder to prevent from occurring and harder to remove once they've been created. So under the surface category, we've got a bunch of different wear modes that can create debris. And these are all because they're wearing at least one of the surfaces that is being contacted by the lubricated parts. So when we have abrasive wear, like I said, that's when one surface rubs against the other one and one of them loses. If there's 3-body abrasive wear, well then we have a particulate in between, but again, at least one surface is going to lose, possibly both. With adhesive wear, we have basically a scuffing motion. We have 2 surfaces coming under contact, and there's a bit more of a pressure gradient here, pushing the 2 surfaces together, and essentially one is going to smear or scuff off material from the other surface. If we've got any form of air entrainment in the oil, we can have cavitation, and cavitation is when these bubbles implode and they impinge upon the metal surfaces, generating more wear debris. Corrosive is simply when we have oxides forming. So as the metals come into contact with water and oxygen, we can form oxides. Those oxides tend to be a softer layer on the metal surfaces. It rubs off a bit more easily. So you will get a wearing surface and you'll be generating corrosion debris. Corrosive wear, as I already mentioned, that's kind of like sandblasting. So that's any particulate impinging on metal surfaces. We've got fatigue wear. Generally speaking, even the most well-designed system with the proper lubricant and everything will run long enough that you will cause fatigue to some of the parts. And as they fatigue, spalls form, and spalls become a contaminant now. Now, funnily enough, when we start hooking up systems to try and keep our lubricated components clean, we might use onboard filtration, or we might even equip it with a filter cart. Well, the hoses that we use to connect things and even the filters themselves are made up of fibers, and some of these fibers will come loose and they can become contaminants within the system. And last but not least, we also have paints and coatings that as they wear, they may generate particulate. Now, these can be often seen inside filter housings and reservoirs. About the only other thing that may generate particulate and is not often considered is the seals themselves. We use seals on tank lids, hatches, whatnot, and I'm not saying those seals are going to generate particulate. But when we use a seal on a rotating shaft, sometimes the seal itself wears and generates particulate, and sometimes particulate gets in between the seal and the shaft. And now the seal actually encourages a faster rate of wear on the shaft because it's pressing the particulate against the shaft. So it's like a form of three-body wear. But I list that one a little bit separate because it's not often considered. Now on the other side, we've got fluid. What can be generated just within the fluid? Never mind the wearing surfaces, the mechanical parts that we're trying to lubricate. Well, depending on the synergies that may be involved here, if we've got significant cross-contamination of two different types of fluids, or if we get something like, say, water in the system, we can actually cause the additives to drop out. And when the additives begin to drop out, they can be viewed as a contaminant because now they're not behaving in the manner they're supposed to behave, and they may take on a slightly different form that can lead to either filter plugging, or just the lack of protection might lead to increased wear. We've got carbon particulate that can be generated. Now, lots of people have experienced this without knowing what was happening, but if you've ever had a system that had rapid darkening of the fluid, and within a matter of a week, 2 weeks, something like this, the fluid has gone from its clear or light yellow color to a very dark color, and you're wondering what has happened, typically when it approaches a black color, it's because of carbon particles, and those can be generated one of two ways. There's either electrostatic spark discharge or microdieseling. And for those that don't know what these two terms are, quick definition: electrostatic spark discharge is when you create a streaming potential on the fluid. Now, if you flow any fluid through an orifice, it will generate static electricity. The question is will it build up to be high enough that the discharge of that static electricity causes burning of the oil? And where it discharges will always be where there's a grounding within the system. So for some people, this grounding may occur within a reservoir. Others, it may occur within the filter housing. Funnily enough, the orifices that the oil is flowing through to generate the static may be the filter themselves, which is why you've probably seen some marketing related to static dissipating filters. One is that they help dissipate static generated from flowing through piping and hoses, but they also know the filter themselves may cause some of this. But when the static builds up and it hits the ground, it will discharge. When it discharges, sometimes that little jump of electricity, it's basically a microburst across a very small distance, almost measured at the molecular level here. But when it's jumping, that bolt of electricity has been measured upwards of 10,000 degrees Kelvin, which is hotter than the surface of the sun, which means it'll burn anything in its path. Now, like I said, the path length is small, so it's not burning a lot. It's just burning maybe a few molecules, a few droplets of oil. But if it's occurring several times per second or even per minute, over time it builds to the point where you've got a lot of burnt oil circulating in your system, and that's where the carbon's coming from. The other form is microdieseling, and microdieseling is called micro because we're dealing with microscopic air bubbles, and dieseling because we're dealing with the diesel process, or what we call adiabatic compression. But basically this is when you're squeezing microbubbles of air to the point that they combust. When they combust, of course, they burn not just the air that they're containing, but they need a bit of a fuel source as well, so they'll burn the molecular droplets of oil they're next to, and again, you get burning of oil, you get black carbon being produced. Now, microdieseling occurs in any system that can have air entrainment, and where the oil undergoes a change from a low pressure to a high pressure. So that can occur within rolling element bearings, it can occur within many pump styles. So there's hardly a system out there that's immune to either of these two effects. Carrying on, one of the other forms of contamination that we produce within the fluid itself is what we generally call oxidation byproducts or insolubles. When these insolubles or byproducts begin to deposit, we give them new names and we call them things like sludge, varnish, lacquer, tar, anything like that. But this form of soft particulate will float around in the system and it can cause damage, generally because as it plates, as it becomes a sludge or a varnish, it will act as an insulator. It can reduce clearances, causing flow issues. So you might get worse heat transfer, you might get lower lubrication because you don't have the oil flow, or you simply start building up heat in the system because, like I said, it will act as an insulator. If we start dealing with some very high temperature applications, or when we've got heating elements involved, we may actually coke the oil, and again, it's another form of a carbon-like deposit. It's very dark. It doesn't tend to cause darkening in the fluid. It is just a very dark deposit itself. But this also can lead to further wear or just a reduction in life on the fluid. One of the other ones that sometimes rears its ugly head that a lot of people don't consider is if you have an incompatible mixture of two different fluids. Sometimes there's a bit of a synergy that occurs here that's not a good synergy, and you will get basically a gelling or a Vaseline-like consistency to the lubricant. At this point, it means it doesn't flow properly, so it may plug suction strainers, it may plug filters, but it also means that you potentially are dropping out some of the good lubricant in favor of some lubricant that is maybe not the optimal lubricant. But those are all fluid-related forms of contamination. They don't necessarily have to equate to small, hard particulate, but they are things that we might consider as a potential. The last category, though, is everything that was built in. And one of the funny things about maintenance is often the more maintenance you perform, the more you introduce contamination. So every time we open something up to perform a repair or an inspection, there's the potential that we've allowed airborne contamination to get in, or we've not replaced a seal properly, or we've potentially damaged a seal that is meant to protect the system. Certainly even something as simple as a top-up of fluid will again provide an opening into the system whereby we might put in more contamination. And that could come from the oil itself or any of the tools we use to get the oil into the system. You know, certainly lots of people leave out funnels, and funnels, when they're oil wetted, they are just dust magnets. And if you don't clean that funnel before you use it, well, you're going to be adding in a bunch of that dust into the system as you pour in your hopefully fresh, clean, new oil. On the other side here, I just listed a bunch of different ways that during the manufacture or assembly of machines, we can have sources of particulate or generate additional particulate during the commissioning or building of a system. And so these are all forms of contaminants or methods of generating contamination within the system. So this is where it's all coming from. Now, funnily enough, we know this, yet we still reach a point where we are running systems and they've got dirty oil in them. So sort of a secondary question I have is, well, why is this? You know, why do we have all these sources being unchecked? So kind of the two big points I like to make with this is, one, new oil is not clean oil. And it's not to harp on lubricant suppliers and say they're doing a lousy job. Let's look at it from the other perspective. What does industry say is the recommended cleanliness for fluid? Well, here's a very popular standard. It's been widely cited. Lots of people use this. It's the ANSI-AGMA standard for industrial fluid. And this is what it has to say about cleanliness. And this is a direct quote. It just says it must be free of visible, suspended, or settled contaminants at the time it is installed for use. So basically, if you pull a sample of your new oil and you have it in a transparent container and you look at it and you don't see anything with your eye, it's considered clean enough for service. Well, like I said, remember that the human eye can detect downwards about 25, 40 microns. that's not the size particles that we know is causing all the damage. That's the size of particles that's large enough that really, it's not that we don't care, but it's not our primary concern. So we've got a very poorly written standard here that many of us are working against to suggest how clean the fluid must be. Funnily enough, we've got an equally poorly worded standard that tells us how clean the equipment must be. Here's perhaps one of the most widely cited documents within the world of reliability when it comes to commissioning. So when we talk about commissioning new equipment, often API standard 614 is mentioned because it is a standard that is meant to help people commission brand new equipment or recently rebuilt equipment. And within it, it's got a statement regarding the fluid cleanliness, or how the cleanliness of the system is judged. So the long and the short of it is they suggest that you flush the system. Now, that's a good premise, but let's read the description of the flush. They suggest the flush takes 1 hour. So they don't give any allowance for the size of the system. They say 1 hour worth of flushing is adequate, provided you meet some qualifying statements. But when they dictate what the 1 hour flush is, they're saying it's only at design flow rate. They're not suggesting this is supplemented with high velocity pumps. They're just saying run oil through the system for an hour and you must yield clean 100 mesh screens. Now, for those of you who don't deal with mesh and just deal with micron, 100 mesh is about 149 micron. So understand that these are screens meant for removing particulate that is 149 or larger in microns. So again, not the size of particulate that we're really wanting to be concerned about. But again, I've quoted directly from the standard here, and it says to further verify the cleanliness, you're going to install 2 to 6 screens. Well, no location information is given about these. They don't dictate that they must be after critical pieces of equipment or that they must be before any installed filters or anything like that. They leave this up to the person doing the flush. And they say the system shall be considered clean when, and they list a bunch of different particulate here, are not visible to the eye and grittiness is not detectable to the touch. Now that's my bolding, not the standards bolding, but detectable to the touch. I would wager that everyone listening right now has probably got a different sensitivity in their fingertips than anyone else. And some of us may be able to feel certain things that other of us can't. But long and the short of it is, if we can agree what size particulate we can feel, I think we're probably all in agreement that it's going to be very large. And of course, it had to appear on this 149 micron screen. So probably the only particulate that is there is a couple hundred microns or larger, which is essentially the size of table salt, which any of us should be able to feel with our fingers. But this is a very poorly written standard in that it's not addressing the type of particulate that we know is actually the most damaging and should be the stuff we want to remove as best as we can before the first time we run the system. So we know we have these issues. We know there's a lot of sources of particulate. We know that much of it can be small, and the smallest is what we want to control, yet this is what we have to work with that doesn't help us get on that path. So to begin the real part of the presentation here, let's talk about understanding particle counts. So how is it that we measure all this particulate? Well, there are 2 different methods for measuring particulate. I'm going to go through what we term optical particle counting first, and then I'll describe pore blockage second. So with an optical particle count, if you were to look up the ASTM standard for this, it talks about the scope and the significance, and it does say it's meant for measuring particle contamination. It lists that it's covering from 4 microns up to about 200 microns, and that's dependent on the particle counter, and you'll see why in a second. But the significance of measuring this size of particulate is we know that this is in the range of damaging particulate, and this is important to us. Right? We don't just want to measure the 149 and larger micron particulate. We do want to get down to some of the small stuff. But understand the cutoff for this test, for the instrumentation used to do this, is at 4 microns. So how does an optical particle counter work? Well, in the most basic sense, you take oil and you flow it through a very thin cell. Now the cell is about 100 micron thickness. So right away you should appreciate that if a particle is much larger than 100 microns, it can't get into the cell. So there are going to be instances where some really, really large particulate might not be measured by this test. But again, that's probably not our most concerning point about the particle count, because that's so large, hopefully it gets knocked out by a filter or it settles out within the reservoir and is nowhere near our clearance sizes. But we flow oil through this cell, and on one side of the oil film, we have an intense source of light. Now, often this is referred to as a laser because it kind of looks like a laser, and we might use the similar technology for generating the light source. So this beam of light is shone through this film of oil. Now, this film of oil is moving, it's flowing, and it's aimed at a photoreceptor. Now, the photoreceptor is the same kind of sensor that we would use in a digital camera. Similar technology to that. What this sensor sees is it sees the light. Now, as a particle goes by, what it doesn't see now is the light. It sees instead a shadow. So this instrument basically sees shadows, and that's what it's using to determine its particle count. It is going to both count and size the shadows. Now, generally, if you've ever listened to a presentation on particle counting, this is where most people stop describing the test. But I want to take it one step further, because there's a very important factor most people leave out of this description that really helps you understand why this is a problem, why optical particle counting has a huge built-in limitation. So most people are probably familiar with the fact that this test counts shadows. What is often said about that is that a lot of other things can create shadows, like air bubbles, water molecules, and even soft particulate like insolubles or varnish precursors. But the more important factor is, how does it size the shadow? This is something not a lot of people necessarily know, or you certainly don't read about this, but it doesn't size the shadow based on its largest parameter. It doesn't size it based on the smallest parameter, and it certainly doesn't size it based on its average parameter. So it's not going by length, it's not going by width, and it's not going by an average. What it's actually going by is something we call spherical equivalency. And spherical equivalency is where it takes the area of the shadow and sizes the particle based on this. So thinking about spherical equivalency just for a second, understand this. If I have a 10 micron by 1 micron particle, well, that's going to generate a shadow with an area of 10 square microns. But like I said, the way this particle counter understands or interprets the shadow is it assumes the particle's a perfect sphere. That's why it's called spherical equivalency. Now, a sphere will make a round shadow, and a round shadow is going to be measured by its diameter. So if you take this shadow that we're looking at right now, 10 square microns, and determine it by spherical equivalency, what you're going to end up with is a 3.6 micron diameter circle, because that would be a 3.6 micron diameter sphere that would create that shadow. Still has the area of 10 square microns. This is the point. So why am I mentioning this? Why do I think this is important to note? Well, what was the one thing we know about this test in terms of its scope? It begins measuring at particles larger than 4 microns. So that particle over on the left wouldn't be reported by this test. It's too small. So right away we need to understand and appreciate that when it comes to optical particle counting, we are not sizing the particles based on any true measurement. We're making a major assumption here that the particles are spheres, which we know they're not, but it's just a nice standardized way of coming up with a repeatable value. But on the other hand, it means that particles could be, and I'm using an extreme case here, 10 microns long and only 1 micron thick, and they would go undetected. Now, in terms of the limitations of this test, for one, it doesn't identify the type of particle. It doesn't tell you if it's metallic or particulate or hard or soft or what. It's just a count. I always joke, that's why the test is called particle count. What more do you expect? And from the scope, it says it measures anything larger than 4 microns, generally up to about 200 microns is the cutoff, because that's about the largest spherical equivalent shadow that can appear on the detector based on the size of particle that can get into the instrument. But the other factor is interferences. As I already mentioned, a lot of people already know this, that when it comes to shadows, other things can create shadows. So there will be some false positives or some skewed high results based on other things being in the fluid. Now, to be fair to optical particle counting, they don't have to be that way. you can dilute the sample with a solvent, and therefore that would help remove some of these effects. By thinning the sample out, air bubbles will come out a bit easier, and if you're using the right kind of solvent, you can cause the water to be more emulsified in the sample, and therefore it won't form the water droplets that will create that refractive difference. It makes the shadows appear. So there is a way around this, but it does require extra steps, and this is often done at the laboratory level. But to be fair to anyone who's considering or already using any form of portable particle counter or an online or inline particle counter, understand the technology in those particle counters is the same as what I've just been describing here. It's a very popular form of particle counting. The detector, the laser, everything largely the same, but your sample prep is different. And therefore, most on-site or online particle counts will be higher than a laboratory one, because labs take these extra steps to help remove some of these effects and give you a true hard particle count. So that's optical particle counting. The other form of particle counting, the one that TestOil prefers, is what we call pore block particle count. And pore block is because we are using a screen that's got a bunch of calibrated pores in it, and we're pushing the oil through at a constant pressure, and we're measuring how much the flow decays. Basically, the flow decays because we're blocking some of the pores. So if we use a screen that's got 10 micron pores in it, the only particles that will be trapped by the screen are going to be 10 microns and larger. Now, as these particles start to build up on the screen, the holes might not be completely plugged up, and there will be fewer holes, and so we're starting to be able to trap smaller and smaller particles. So what we do is we actually do a profile of this flow decay, and based on how fast the flow decays, we know how many particles are there and sort of what the distribution looks like. But to be fair, this is the big limitation to this test. The distribution of particulate is extrapolated, and it's assumed to be a fairly linear distribution. So if you're doing any form of filtration on the system and you know you're removing a certain size particle and up, well, we're basing our measurement off whatever the pore size of the screen might be, which is typically 5, 10, or 15 microns, and we're extrapolating all data from there. So it might not give a representative view of your filtration activities in terms of an exact shift at a certain micron size. You will still see it because the particle count will be lower. You will know it's being effective, but you might not get quite the nonlinear distribution of particulate that you would expect based on your filter. So both optical particle counting and pore block particle counting have their own limitations, which we can usually live with. The cool thing about pore block, though, is it doesn't have the same interference that optical does, which means we don't need anywhere near the sample prep. So it's a much easier test to get repeatable, and that's the important thing. But that leads me into the next question. How repeatable is a particle count test? And going to the ASTM standard for optical particle counting, which has had an interlaboratory study done, this is the data they've published. And the long and the short of it, I've underlined at the bottom. What this means is that if you look at the reproducibility values, which is basically the same sample split between two labs, we have around 100% or higher variance in the data, which can, not necessarily will, but can account for up to a 2-code difference from one particle count to the next. I mean, 100% will definitely be at least one isocode variance, but it can potentially mean 2 codes. So hold that thought for a little while. I'll address it again towards the end. But when we talk about particle counting, we do talk about isocodes all the time. And isocodes are not necessarily widely understood. So let me segue here and talk about the results just for a second. So how do we get an isocode? Well, when we do a particle count, we do the count in various sizes and ranges. The 3 ranges that we use to determine a code are greater than or equal to 4 microns, 6, and 14 microns. Now, the important thing to note about these 3 ranges is that if I count a particle as being greater than 14 microns, I'm certainly going to count it again as being greater than 6, and I'm going to count it again as being greater than 4. So as such, the 4 micron particle count is always the highest count, followed by the 6, followed by the 14. Just think of these ranges as essentially 4 to infinity, 6 to infinity, 14 to infinity. Now it's not really infinity, but the point is it's not 4 to 6 microns, 6 to 14 microns, and then 14 to some other value. It's basically everything larger than 4, everything larger than 6, and everything larger than 14. So it's what we call a cumulative count. Now these three ISO ranges are now coded, and this is where the confusion tends to set in. So we need to take an actual particle count and turn it into a code. Well, ISO comes along and it gives us this table on the left, these lovely ISO codes. Now, if you look at either of the two tables on the right, those are examples of a particle count. So you can see how the particle count is pulled from the ISO codes. So in these two examples, the top right one says a particle count of 151,773 particles per milliliter. If you look to the left in the table, that falls between 80,000 and 160,000, which is given an ISO code of 24, and you would code that 151,000 as an ISO code of 24. And you can keep reading down the list. You can see the little liter lines in between each one as it corresponds. So the long and the short of ISO coding is you take a count and you look it up according to this chart, and it'll tell you what the number is to assign to it. Now, I'll get to that in just one more slide, but as a quick note about ISO codes, if you notice the pattern of how they came up with the code to match the range, just start looking from the bottom of the list upwards. So when you get to an ISO code of 10, it means you have between 5 and 10 particles per milliliter in the sample. If you go up a code to 11, it now doubles to 10 and 20. So the values are doubling every time you go up an ISO code, which not only means you're counting twice as many particles, but the overall range of that ISO code is twice as large. So you get some pretty large ranges as you get into the higher ISO codes. So using this table just for a second, the one on the left, and coding results, let's walk through an actual example, not just the ones that appear here. So if I present to you this data, and I show you your first, your second, and your third sample, you can see the particle count data below, but I've left the coding blank. Now to code these, what you would do is you'd look up each one of these values on the preceding chart, and you'd find the code that goes with each count. So as an example, 1357. Well, that falls between 1300 and 2500, which is an ISO code of 18. So the very first number I'd write is 18. 361 particles is between 320 and 640. That happens to be an ISO code of 16. So the next number I'd write would be 16. And then 42 falls between 40 and 80, which is an ISO code of 13. So the last number I would write is a 13. So that first sample would code out as 18, 16, 13. Well, funnily enough, if you try the second sample and the third sample, they're all going to work out to 18, 16, 13. And that's kind of the point of ISO. Because why did we take one set of numbers you didn't understand and turn it into another set of numbers you still didn't understand? The point was that we tried to group the numbers so that we could see, relatively speaking, when they were similar. And all three of these particle counts are viewed as in the same ballpark as each other. So ISO says there's really no difference between these particle counts. That don't dig in to the few hundred particle difference that you're seeing here. To them, they're all within the same ballpark. But like I said, we took one set of numbers and turned it into another set of numbers, and 18, 16, 13, well, that's a nice set of numbers, probably still doesn't make any sense. Right? You're looking at that going, well, is that clean or is that dirty? I don't know. So thankfully, somebody tried to address this, and Caterpillar came along, they did a nice study, and they found that it would take about a teaspoon of debris to contaminate an entire 55-gallon drum to a level of 18, 16, 13. So now I can use this. I can go, okay, if I see a particle count of 18, 16, 13, that roughly equates to a teaspoon of material in 55 gallons. That is tangible now. I can now take a particle count and work with that. So let me give you another example here. On the left, we've got typical cleanliness of new oil, which, depending on the sources you read, is going to be about 20, 19, 16, give or take an ISO code. Well, 20, 19, 16 is 2, maybe 3 ISO codes higher than 181613. So if you understand ISO codes and that every time you go up 1 code, you double the particles. When you go up 2 codes, you double it again. And when you go up 3 codes, you double it yet again. It's suggesting that a 2019-16 would in fact be about 4 to 8 times dirtier. So 4 to 8 times a half a teaspoon means you've got between 2 and 4 teaspoons of debris in every drum of new oil you've ever purchased. Now, if you compare that to used engine oil, which is what I've got on this slide, that's yet another 3 ISO codes higher, which is another 8 times increase in the amount of material. And what this means is that we could have between 16 and 32 teaspoons, which is between, a pretty wide range of material here, but still 16 teaspoons, that's a lot of debris. Now that's probably more soot than it is metallic wear, but the point being, it's a pretty significant amount of material, and that's what 8 times dirtier looks like. Now, if you can appreciate that 8 times dirtier, hopefully you can appreciate this. Imagine you take that new oil, which I said has between 2 and 4 teaspoons, roughly speaking, based on the Caterpillar study, and we try and put it into a hydraulic system. Well, a hydraulic system is looking for oil that has an upper limit, 16, 15, 12. Well, that is 4 ISO codes higher. So that is 16 times dirtier. So our 2 to 4 teaspoons are about 16 times more debris than we're looking for. We're wanting, a quarter of a teaspoon, maybe an eighth of a teaspoon maximum per 55 gallons. So this just goes back to when I said sometimes the contamination is due to the fact we've added oil. And it's not necessarily that we use dirty tools to add the oil. Sometimes it's that we didn't pre-filter the oil going in. So we need to appreciate what an ISO code means, how you interpret the ISO codes, basically every time you go up a code it doubles, to understand where we are and where we want to be. Now just one quick little reference, so it exists in the slides when you get a copy of this at the end, but there are more than one way of reporting particle counts. So I just threw in a little bit of writing here about NAS and SAE, 2 different reporting styles. It's the same technology for measuring the particle counts, just 2 different ways of reporting it. So this slide exists so that you have it as a reference after the fact. But what I'd like to move on to is, well, why does my particle count go up? Right? We know how we measure the particle counts now. We know all these sources of particulate. So that's going to be obvious to us then, where does most of this come from, right? Most of the particulate that we're seeing has probably been ingressed from the outside, or it's been generated on the inside due to wear mechanisms. So if it's been ingressed from the outside, we know the list of possible sources for that, and we know the reasons, right? It's anything that breathes, any opening, dipstick, fill cap, patch cover, you name it, any path it can find, it will go in. But what else causes our particle count to go up isn't necessarily a mechanical issue. Could just be where or how we sampled it, right? If we don't flush the sample point fully, or we don't wipe the debris around the outside, we may get particulate in the sample bottle that's not really representative of the fluid flowing in the system. One of the other ways we get an increase in particle count is when the filters don't function. Now, if the filters go into bypass for any reason, I mean, it could just be that the bypass was left open, or it could be that they're starting to plug up. We will expect that we're no longer mitigating the increase in particle count, and that we should expect as new particulate is ingressed or generated, the particle counts will slowly rise. But one of the other factors that comes up is when people start plotting particle counts. They start to notice a pattern based on filter changes. Now, this is the most common pattern that we see, right? The sawtooth pattern. We'll see an increase in particle count, then we get a drop, and then it'll increase again, then we get a drop. Now, the assumption is this is when we change the filters, that every time we change the filters, we will get an immediate drop in particulate. What I'd like to share with you, though, this is the reality. One company I used to work for a number of years ago was a filter company and was doing some research, and we were trending particle counts. And what you notice is that in many systems, the particle count actually increases immediately after a filter change, and then it begins to decrease. But the problem with seeing this pattern is many people have now attributed this little bit of a rise before the drop as filter efficiency. And you'll hear people comment that, well, new filters aren't as efficient as used filters. It takes them a while to block off the big holes. I'm here to tell you that's not the reason. The biggest reason you see this pattern here is when you use cartridge style filters, not spin-on style filters. And many of us use cartridge style filters. And the big reason that you see that increase is because, as I like to point out about filters, filters stop a lot of particulate. They don't necessarily trap the particulate. So when you have a filter housing with a cartridge filter inside of it, oil goes in with particulate and oil may come out without that particulate. And the particulate is somewhere within the housing, but it's not necessarily trapped inside the filter, so that when you change the filter, you're not necessarily removing all that particulate. And what you may get, and hopefully what is clear in this picture, is what you will get is on the outside of that reddish brown ring that you see in the picture, because we're looking straight down into a filter housing, you will have on the outside of that reddish brown ring the dirty oil, and you may have a collection of debris there. Now on the inside of that reddish brown ring is the clean side of the filter, because that reddish brown ring is where the filter should be seating. Now all this particulate that is occurring on the outside of that filter, that's not a big problem. But when you do not drain the filter housing before you remove the filter, when you pop it off the bottom of the filter housing, oil is going to sluice from both sides towards each other. And you might get some of that particulate on the dirty side of the filter washing itself over onto the clean side of the filter housing. So now when you install the new filter, even though you've got a nice new filter, there's a bunch of debris on the clean side that's going to have to take a ride through the system before it gets to the filter again. Now, in this extreme case that you're seeing in this picture here, there may be enough debris that that new filter is not even going to seat properly, and you will have a bypass occurring at the bottom of the filter, meaning a lot of that particulate now may start running through the system. But it's just one more reason to point out why a particle count might go up, and if you're trending particle counts very frequently, you may notice that immediately after filter changes, the particle count does actually continue to rise, might even spike a little bit, and I'm just suggesting this is one of the causes. Now, something of quick note here, the pitfalls. Just a few notes about why people misinterpret increases in particle counts. Again, going back to how or where you sampled it, that's one thing, because if you see a lot of particulate in the sample, but you don't see a lot of corresponding wear, question is, why wouldn't all the particulate or contamination cause the wear? It's because, well, maybe it's only in the bottle, it's not in the system. So when you don't wipe the outside and a chunk falls into the bottle, it will show up as part of the particle count. It doesn't mean it's within the system, and you get these sort of atypical results. Also, sampling from dead legs tends to do this too. But the other thing, the big pitfall with particle counting is this. A lot of people will look at an increased particle count and they will immediately look to the elemental spectroscopy, and they will wonder why they don't see an increase over there. They go, well, if my particle count's going up, why is my iron or my silicon not going up? Because iron being the most common wear element and silicon being the most common form of contamination. People look for that correlation all the time, but funnily enough, these two tests don't actually overlap that much. Particle counting is 4 microns and larger, whereas elemental spectroscopy typically measures accurately in the 0 to 5 micron range. Between 5 and 10 microns, it loses its accuracy significantly, and pretty much anything above 10 microns is not measured accurately at all. So these two tests don't actually overlap, and that's a very common mistake people make when interpreting them. So there we have how we do a particle count and sort of how we interpret the results, generally speaking. The last and final question we have then is, well, how do you set a target? How much is actually allowed? Well, again, reiterating, new oil is not clean oil. So we know that we are probably not even starting off with oil that is clean enough for what we need. And when we're setting these target cleanlinesses, they apply to the new oils as well as the running system. And like I said earlier, new oil is typically around a 20, 19, 16, give or take an ISO code. And that tends to be significantly higher than most OEM recommendations. And when I say at least 8 times dirtier, it's because it's at least 3 ISO codes higher. But just to give you another visual here, here's your new oil on the left compared to hydraulic fluid under running conditions on the right. Pretty big difference in cleanliness. So we need to set a target. So to wrap up our presentation, it won't take long for me to show you this, but here's how you set a target cleanliness level. Generally speaking, what you should use are some chart or table. The one I've reproduced here is from HiPro. The numbers on it are not a whole lot different from any other source, so I'm not using HiPro's because I think it's got the best or most realistic numbers. Why I like HiPro's though is that they actually have an extra column of information that most of these charts don't include, and it mentions the micron rating of the filter. Now, obviously, because it's coming from a filter supplier, it's because they're trying to sell you filters and let you know what sort of filter selection you might want. I just use it because it helps me identify if I'm setting a reasonably achievable goal. So you'll notice that these charts are listing a bunch of components, not a bunch of machine types, right? It doesn't say compressors, gearboxes, hydraulics, pumps, anything like that. It's specific to the type of components because this is how you set a target cleanliness. It doesn't matter what the overall machine is or does. What it matters is what's it built with. What's inside of it that's lubricated. So I've reproduced the chart here. It covers 2 different slides. So you've got 2 different slides worth of information here. But here's the example I'll walk you through. What would be the target cleanliness for a system or machine that includes a variable piston pump, a servo valve, and a high-speed journal bearing? Now, this system operates at over 3,000 psi, this hypothetical system we're talking about. So we can go back to these charts and look up the data. So if you look at the first table there, the one labeled pumps, variable piston pump is second from the bottom line. If you go to more than 3,000 psi, way off to the right, you will see it recommends an ISO cleanliness of 16, 14, 12. So keep that number in your head for a few seconds here. If you look at the next table at the bottom, servo valve is the very bottom line. And servo valve operating above 3,000 psi suggests an ISO cleanliness of 15, 13, 10. So hold that number in your head just for a second. And the last thing we said was it had a high-speed journal bearing, which you can find in the top table. High speed's the middle row. If you scroll all the way to the right, there's only dashes for the data at above 3,000 psi. So we're pretty much stuck using at the lower pressure, but we see it's 17, 15, 12. So what we got from the table is this. 16, 14, 12 was the value that the variable piston pump said was the required cleanliness at greater than 3,000 psi. 15, 13, 10 was for the servo, and 17, 15, 12 was for the high-speed journal bearing. So how you pick the target then is which one is the lowest. So 15, 13, 10 is the lowest. That is the required cleanliness to properly protect the servo valve. So if it can protect the servo valve, you know that cleanliness is more than enough for the variable piston pump and way more than enough for the high-speed journal bearing. So now we have a reasonable target. But like I said, why I like the high pro version of the chart is it also mentions what kind of filter we might need to do this. And if you were to go back to the charts and look up the filter for a 15, 13, 10 particle count to be achievable, it's recommending a 5 micron or better, finer filter to achieve that. So like I said, what this helps me understand is that if I'm not using at least 5 micron filtration, I can set a 15, 13, 10 target all I want, but it's going to be very hard for me to achieve that. So I need to couple, temper my expectations with reality here and say, well, what's the point of setting a target I can never hit? And either I increase my target to something that is achievable and understand that maybe it's not the optimal or best performance, or I now have to consider better filtration and all the consequences that come with upgrading filtration. So the last thing I want to leave you with is this. This is a target. This is what you're trying to hit. It's very different than when you're doing oil analysis and you're reading reports, because when you're reading reports, you're not looking for the target, you're looking for the limit. And how you set a limit is essentially this. Whatever your target is, you should go 2 ISO codes higher. The target and the cleanliness should be 2 ISO codes apart, is what I'm saying. And why this is as I already pointed out, the test is only accurate to within 1 ISO code as it is. So you have to give yourself that much wiggle room to begin with. But the other thing is, if you don't allow yourself at least 1 more ISO code in terms of a tolerance here, you're going to be constantly in alarm, or you're going to be constantly having to address the situation. So give yourself at least 1 ISO code extra, and that way, until the particle count truly increases from its target value, you're not having to perform a corrective action, whether that be, change the filters or add a filter cart or whatever it might be. But targets and limits are 2 different things. So please, when you go through an exercise of setting a target cleanliness, don't ask the lab to set the same value as your limit, because chances are then you will be constantly in alarm, or you'll be trying to overachieve what is not necessarily required, right? So it's just in one way or another more effort that needs to be addressed. So with that, I think I can say thank you and turn it over to Taylor to see if we've gotten any questions along the way that need to be answered at this moment in time. But other than that, I do thank you for listening. And if you don't want to stay on the line and ask any questions or use the question chat box there, you can always email me directly. So thank you.
All right, thank you so much, Evan. And we do have a few questions here. All right, first one here. Will there be a big difference in value of an oil sample if sent in with minimal information of equipment versus providing make, model, gear ratio, etc.?
Well, the numbers are the numbers. So the data is measured the same way regardless of providing a bunch of information. You may get a slightly different test if we don't know the machine type. But again, as long as we're talking about the same test data, the numbers will be the same. It's the interpretation that varies if you don't provide a lot of information. But no, if you sent us a bottle of oil completely unlabeled except for your customer name and an email to give you the results, you would get, as an example, the exact same particle count than if you told us it was out of a 1993 Camry with 15,000 miles on it and so on and so forth. So no, the data, essentially the lab operates blind. The people producing the results don't know and don't need to know any of the information. It's the analysts who review the data at the end where that information gets taken into account.
Okay, another question here. I've heard it said that a dirty filter will filter better than a new filter. True or false?
It's not that it filters necessarily better, because that depends on how you define better. But yes, as a filter plugs up its larger pores, arguably then the remaining smaller pores will filter finer and finer. Problem is that as you've plugged up more pores, you've decreased its overall efficiency and capacity, so you're not getting the same flow rate through it, and you certainly don't have as much remaining filter life to it. So it's a bit of a misnomer, it's a twist on wording here, because it's not that it's necessarily worse and it's not that it's necessarily better. It's all about perspective. So no, I would kind of say false, because I don't like the implication when people think that a used filter is better than a new filter. No, new filters are better than used filters. A new filter has all the pores, all the oil flow, everything going for it. It will operate as per design. A used filter is, of course, less than design. It's in some way inferior. And like I said, it could be perceived as flow rate or capacity, not necessarily pore size. So that's kind of a personal take on it. You'll always find people who disagree with that statement because they say, oh, it's better, of course, because it's got smaller holes in it now. I'm like, yeah, but think about that logically. What are the holes that are likeliest to plug up first, right? Usually the small ones anyway. So I don't really think you're getting ahead of the game there, but either way. Any other questions, Taylor?
Yes, we have one more here. How would you verbalize the difference between the two following ISO codes, 18, 16, 13 versus 18, 15, 12?
Well, how you verbalize the difference is that the 18, 16, 13 has twice as many particulates, 6 micron or larger, than the 18, 15, 12. And the reason you verbalize it that way is the 18 is the same for both, so you can't apply the statement to 4 microns and larger. But since both the 6 and the 14 micron particle counts were one ISO code higher, the 1613 being higher than the 1512, and one ISO code representing double the particulate on average, that's how you would verbalize it. So it's got twice as many particulates, 6 microns and larger.
All right, it looks like there's a few more questions here, but I feel like they'll be better answered through email. I'd like to thank everyone for joining us today, and thank you very much, Evan, for presenting.
All right, well, thank you.